simple example. Our determinant formula. So I don't know. I think I said we can consider this graph. So let's consider cycle graph. G. So this cycle graph has n vertices and n edges. So it has okay. So this cycle graph has 2 primes, right? We have 2 primes. 1, 2, 3, 4, and so it has got 2 primes. One is 1, 2, 3, 4, and the other one is we can just come the other direction, and they are not equivalent according to our right? So we have 2 primes. So the set of primes is finite, right? So then this zeta function, remember, it was a product of 1 minus u LP inverse. This was over the set of all primes, right? Okay, so this product has 2 terms then. So this is like 1 minus, and length of each prime is n, right? So it's un minus 1 times 1 minus un minus 1. So that's equal to 1 minus un minus 2. So that's this one. Now, on the other hand, the right side of the formula, sorry. So to compute the right-hand side, we had to compute 2 matrices, A and Q, right? So matrix A was adjacency matrix. Adjacency matrix. So this matrix is n by n, and okay, so 1 is connected to 2. So so A, I said bi. So let me put it like aij is equal to 1 if I is connected to j and is 0 otherwise. So for example, 1, 2, it's so here is 0, then there is 1 here. But then 1 is not connected to anything except there is also 1. 1 is connected to n, so we put 1 here. And then, so 2, of course, is connected to 1. I mean, the matrix is going to be symmetric anyhow, so this is this. And then 1 is not connected to 3. Sorry, 2 is connected to 3. Here is 1. And then 2 is not connected to 4. But 2 is connected to 1, which is here. So the form of this matrix, then you can see that on the diagonal is going to be on the diagonal it's going to be 0. There are 1s here, and it's a symmetric matrix, so there are 1s here as well. and it's symmetric, so there's a 1 here as well. Right. This is there because n is connected to 1. So got this. So this is matrix A. And what is matrix Q now? So matrix Q is, it was a matrix Qij where the valency of the vertex I, it was Qi plus 1. So this is matrix Qi. So this is the matrix. And valency, so this is a regular graph, its valency is 2. So Qi plus 1 is equal to 2 for all I. So Qi is equal to. So this is identity matrix. Just it's simple. Okay. So then the right hand side, we can just say that. Remember, we have to look at the determinant of 1 minus UA plus U2Q, right? So we have to compute the determinant of, okay, 1 minus, well, this is identity. So this is 1 minus U2, identity matrix, or 1 plus U2, sorry, identity matrix, minus UA. And the claim is that, so the determinant formula in this case, the determinant formula in this case just says that this guy, 1 minus un to the power 2, remember, so, okay, what was it in general? It was that zeta g u inverse was equal to determinant of this guy. Oh, I'm not out of, I am almost totally out. So this is equal to determinant of 1 minus UA plus U2Q. So in the case that we have a very concrete identity. We must have, in other words, 1 minus un, sorry, squared is equal to determinant of 1 plus U2 identity minus UA. Okay, I mean, it's a nice exercise to prove this directly in this case. It's doable, right? So exercise is prove it directly. Without using anything. So it's doable. Let's check if this makes sense, because we have got now, this is a polynomial, just let's check the degrees at least. This is a polynomial of degree 2n, right, on the left-hand side. On the right-hand side, we have this matrix in diagonals. It's like 1 plus U2. And there is some u's here, anyhow. So what? So what is the determinant of this guy now? Well, there is this leading term here, which is I can just multiply 1 plus U2, 1 plus U2, 1 plus U2, right? So we have got 1 plus U2, so degrees match at least. Okay. So that's the simplest thing I can, that's the only thing I can do right now. So degrees on both sides match. Okay, degrees of the two. So this is not totally outrageous, at least. So that's okay. So that's okay. I think that's about the only thing I wanted to say about this Ihara. So now the thing is, as I said, how do we use this formula to prove statements about graph prime theorems, and for what graphs Riemann hypothesis is true? These are the things that we'll have a talk about. So this is example of really a nice identity that relates primes in some sense, classical mechanics or geometry to essentially spectrum of Laplacian, although I mean I said this is only the case in the case of regular graphs, but that's still pretty. So I think I'm going to leave it at that and then start now talking about trace formulas in general. So
can I ask a question?
Yes.
So when I was thinking about like what kind of information the Ihara zeta function encodes, then I thought it doesn't seem to be just topological information, because there are certain graph transformations, like you contract an edge, but it will change the zeta function a lot. So apparently the lengths of the primes are very important in the zeta function. So like I mean, the question was in my mind, there was is the zeta function invariant under all the transformations of a graph that we care about?
First of all, I mean, the zeta function, I mean, Ihara is not topological, it's very geometric, right?
Yeah.
Because lengths of geodesics are important. But your question is it invariant under isomorphisms of graphs? Yes. I mean, if you have two graphs isomorphic, then all the structures are going to be the same. I mean, primes are going to be the same. You can just transform the things. Yeah. So that's what it is. Yeah.
Okay. Thanks.
No problem. So I mean, yeah. Okay. So let's. Yeah, this is a very good example. I mean, it's really something that we can work with kind of concretely and. Okay, so there is this discussion of trace formulas in general now. So let's start with kind of a general form of Poisson summation formula, and then we will get to that. So the first part is general Poisson summation formula. Okay, so yeah, so we need a little bit of background about free analysis on locally compact abelian groups. So this is, let's recall Fourier analysis on locally compact abelian groups. Okay, so let's assume, let G be a locally compact. So this locally compact abelian groups, I just write it as LCA, locally compact abelian. LCA group. So the first thing we have to understand is duality for such things. So the characters. So a character G is a continuous map chi from G to the unitary group, simple group in this case, continuous. But it has to be a group homomorphism. Group homomorphism. So of course, if you think additively on G, I mean multiplicatively about G, then this means chi of G1, G2 is equal to chi of G1, chi of G2. And if you think additively, you just write it as chi of G1 plus G2 equal to chi of G1, chi of G2. So that's both cases are can be used. So then the notation in this case is that we let G hat okay, so yeah, so let G hat be the set of all chi is a character on G. Okay, so this G hat, of course, is a group. You can see G hat is called dual group of G. When you check that it's a group, is a group, I mean, you can just easily check that this is a group under pointwise multiplication, for example. And in fact, it's a topological group. In fact, it's a locally compact, well, I mean, it's abelian. That's here. But it's also a topological group, and in fact, is a locally compact topological group, and is locally compact. So this is a theorem. I mean, you have to prove it. This is a theorem of general topology. You have to prove this. What topology you choose? The topology that you choose is the topology of function spaces. So you just say G hat is inside continuous functions from G, space of all continuous functions from G to U1. So the topology you use here is compact open topology. So this compact open topology gives you a topology on G hat, induces topology on G hat, and we are saying it's a fact, it's a theorem that it's again locally compact abelian. So this dual group again, you go from category of locally compact abelian groups to locally compact abelian groups. And this duality is very nice because there is this Pontryagin duality in this case. Duality theorem. It says that this canonical map from G to G double hat is an isomorphism. Canonical map. G double hat. So you have this group, locally compact abelian group G hat. You can apply hat again. You get this group, and there is a natural map, of course, from G to G double hat. It's easily seen to be injection. but actually it's an isomorphism. It's a surjective anism. Is isomorphism of groups. It's continuous, inverse is continuous, and all that. Okay, so that's one thing. Now we want to do Fourier theory on these things. So there is this. So let me give you some examples. Of course, the simplest example is G equal to cyclic group of order n, Z over nz. The cyclic group of order n, this group, it's a dual. It's isomorphic to, again, cyclic group of order n. This is not very good to write it like this, but that's fine. This you can easily convince yourself that's true. In fact, what's the map? I mean, if you have a character here, so if I have any character here, I of class of say some element k is necessarily going to be of the form. You can show that this is going to be of the form c to the power 2 pi I over n. So let me define it like this. Let chi of this to be k. Yes. Then you can show that any character on this prime is of the form chi to some power n for some n less than n bigger than or equal to 0. It's of this form. It's power of this basic character. And this character is obtained by fixing this root of unity. So you can say that the group of characters in this case is isomorphic to nth roots of unity. So maybe you can just replace that by mu n, the nth roots of unity. Anyhow, so that's first example. Of course, the second example is going to be the group G equal to R. In this case, any character is going to be of this form. Chi of t is going to be of the form e to the 2 pi I s t, or a unique s in R. Unique s in R. You can prove this. I mean, it's an interesting result using the definition, using continuity and just also the definition of the character. You can show that any character of R is of this form or a unique S in R. So this in particular shows that R hat, the dual group, is isomorphic to R under this map. Okay. So that's another example. Another example, you can think of G equal to Z, and then you can take its dual. This is isomorphic to S1. And any character here of the form chi of M is e to the 2 pi I theta and for, well, I mean, you can just say, so let me just not write it like this, let me write it as c to the power n for a unique c belonging to S1. I mean, this c is not the root of unity now, it's an element of this. I can always write it like L to the power n. Yeah. We can also write it like this for a theta which is fixed modulo interval 0 to pi. So open. Okay. Then you have. So in all these cases, you can directly check Poisson duality, but in general, it's a very deep and it's a theorem which is very difficult to prove, actually. There are several proofs, all of them are difficult and non-trivial. So the original proof was very, very difficult. The way Poisson proved it, he reduced it to a special cases. So it was very, yeah, I mean, it was a very, very difficult statement. Okay. So now what we want to do is Fourier transform. So one of the things that, another thing that I need beyond the character is the idea of Haar measure, right? So, so we need this notion. Before talking about Fourier transform, Haar measure on G. So, okay, so Haar measure we know that exists and is unique. So left and right. Because it's abelian, there is no difference between left and right, invariant measure on G. It's unique up to a multiplicative constant. Unique up to a constant. This is a theorem. Again, it's a deep theorem. Existence of Haar measures in general for all locally compact groups, not necessarily abelian. We know that it's true. And in the case of abelian locally compact groups, maybe there is an easier proof, I'm not sure, but still, because this still in the abelian case, there are many, many possibilities. So I don't think, yeah, maybe the proof is easier, I don't know, but I'm assuming that this is Haar measure. So, so given G, fix a Haar measure on G. Then this Fourier transform originally is defined as a map from, say, L1 of G to continuous functions on G hat. And they are defined like this. So this is the Fourier transform. So the way you should think about Fourier transform in the abelian case is that it's a map that takes functions on G to functions on G hat on the dual group. So it's a duality, right? So how does it work? So it sends F to, say, F hat, where F hat of, say, a character chi is equal to integral over G F of little g chi of G at in G. Okay. So this is the Fourier transform of this function. Because f is L1, and these guys have absolute value 1, so this function, when you multiply, is still L1, so you can integrate. And continuity follows from the fact that this f is a continuous function. I mean, the character is okay. This continuity maybe it's not so obvious, but I think it's not difficult to prove the continuity. But what is very difficult to prove, again, in this case, is So this is Fourier transform in general. Well, in general, in the abelian case, right? In the non-abelian case, is even. Well, we have to deal with non-abelian soon, but this is the abelian. So what is interesting in this case, there is this Plancherot theorem. What is Plancherot? It just says that for any f belonging to C0 G, this norm 2 of f is equal to norm 2 of f hat, where norm 2 of f squared is equal to integral of absolute value of f of g. It's L2 norm. dg over g equal to, so okay, it's, okay, now, the right-hand side, I haven't defined it yet because I haven't fixed the Haar measure for the right-hand side in order to define the L2 space. It's part of the statement of Plancherot theorem is that for a suitable Haar measure, it's not that this is true for any, I have fixed the Haar measure on the left-hand side anyhow, but it's not true that for any Haar measure you pick on the dual group, this equality holds. It has to be for a suitable Haar measure. I mean, it's true up to scale, but for a suitable Haar measure, it's equality always. That's this statement on G hat. Okay? Thus, Fourier transform extends to a unitary isomorphism between two Hilbert spaces, right? To a unitary iso. Again, I denote it by this from L2 of G to L2 of G hat. So that's part of the statement of Plancherot theorem. And moreover, the Fourier inversion formula is holds in this generality. Fourier inversion formula. So what is it? The Fourier inversion formula tells us how to recover f from f hat. It's the inversion formula, right? So
Masoud, why f hat is in L2?
Sorry?
Why f hat is in L2?
It's part of the statement that it is in L2 and the L2 norm is equal to that. Yeah, because left-hand side is finite, and the statement is that this is it's part of the statement of the Plancherot theorem. Yeah. Right. Okay. So moreover, this we have we can recover so f of g is equal to integral over g hat f hat of chi of g dg d chi, sorry. Yeah, so there is no bar here in this case. You see, you're integrating the Fourier transform over the dual group like that, and this is the Haar measure that's guaranteed by first part. Right. So, Now, what examples, of course, well, I mean, if G is equal to R, the theory is the theory of Fourier transform. So this is the classical Fourier transform theory on the line, or G equal to Rn also. And that's also, I mean, G hat, again, is isomorphic to Rn. However, you have to be careful. So part of the statement is that the measure on G hat is also fixed. In this case, for G equal to R, if you choose Lebesgue measure for the left-hand side, in mu equal to Lebesgue measure, I mean the x equal to Lebesgue measure on left-hand side, on R, I mean, we have to use 1 over 2 pi Lebesgue measure for the right-hand side. Need to use 1 over 2 pi dx on R hat isomorphic to R. Well, the isomorphism, you know, under the isomorphism that sends the character chi of x equal to e to the 2 pi I s x. This character chi s, which is by definition e to the 2 pi I s x for all x belonging to R, chi s is sent to s belonging to R. So if you use this isomorphism, R hat with R, that I'm writing here, then under this isomorphism, the R measure on R hat corresponds to 1 over 2 pi dx. So with this kind of convention, we can forget about the dual group, and that's why usually in elementary presentations of Fourier transform, you don't see G hat or R hat. You just work, you say you have a map on R, a function on R, you send it to function on R again. But the reason is secretly you're using this isomorphism. And in general, you cannot do this, you have to work with G. So this was example 1. I mean, example 2 is something which is even more familiar because that's Fourier series, right? So this is example 1. So we get EG2. So just choose G equal to S1. Right? In this case, as I said, G hat is equal to Z. And this is the theory of Fourier series. So a 2 pi periodic measurable L1 function, right? F is mapped to F hat. In this case, F hat is a function here, so all that matters is the value of this function F hat on N, which is this, is F of X. The character corresponding to N is e to the negative 2 pi I N X dx. So we are thinking of this as R. No, this is Z. That's fine. Yeah. So we are thinking of this as R mod Z. In other words, this is integration over one period. So, And of course, Plancherel formula in this case is this famous formula that integral f of x squared dx from 0 to 1, right, is equal to sum. Now I may have to change things here, but let's see. Equal to sum absolute value of f hat of n squared, and from minus infinity to plus infinity. So this is this. I mean, this is the counting measure on the dual group. That's the Haar measure in this case. It's the counting measure on the dual group. Now the thing that I have fixed here is the measure here is so if I identify this with interval 0, 1. The length of 0, 1 is 1. So that's the measure of the total space is 1. And that's a normalized Haar measure. So for here, I use normalized Haar measure. And so the Plancherel theorem in this case is this statement. And that multiplicative constant is 1, it turns out to be. I mean, it could have been something different, but you're lucky it's just 1. Right? So that's some basic thing that we need to use in order to move forward to.
Can I ask you a question, please?
Yes.
So I didn't get a part. You wrote a gamma from L1 of G to C of G hat. And then you wrote another one from L2 to L2, and you said this one is extension of the other one, but L1 is not in L2. How you want to extend that?
It's not. This is not a question of being in L2. The thing is, I use CC of G. You're not paying attention at all. I use CC of G. This is dense. This is compact support function. This is dense in L2 of G. And the map is used to preserve, yeah, you have to pay attention. CC of G is dense in L2 of G, so that's okay. Right. Okay, so that's what it is. Now, can you give me an example of a locally compact abelian group which is not one of the things that I have discussed? Huh?
Or n divided by that. I mean, it's the same as.
These are the ones that I discussed. No. Give me an example of a locally compact abelian group which is really different from these things that I have given here.
Like a function space, I guess.
Okay, so that's yes, Jeremy, that's a good try. Functions from where to where?
Like continuous functions on a compact space through complex numbers.
And okay, so let's look at continuous functions from M to complex numbers.
Oh wait, this might not work.
Yeah.
Yeah, never mind.
You need a group, and also you need the locally compact topology.
Some Lie group like SUN or.
Or they are not abelian.
Oh, right.
That's not abelian.
Probably means some p-adic nonsense.
Yes, exactly. So p-adic is really goes to the heart of the matter from perspective that I want to look at. So let me give you this example because just you're having a little bit of fun with these things. So QP, so p-adic numbers. So this is field of p-adic numbers. So what is it? This is completion of, I mean, it's the metric completion, right? Metric completion of Q with respect to p-adic metric. This is the p-adic metric. So p-adic metric of a rational number like a over b is equal to p to the power minus say m, where where this m is obtained like this. So p to the k. So first of all, write a and b in the simplest possible form. I mean, there's no common divisor between the two. Then we are saying p to the k divides a, and p to the l divides. There is some k that p to the k divides l. There's some l that p to the l divides b, and then m is just k minus l. And then you invert it. So this is an ultrametric. So we're getting a little bit sidetracked, but that's okay. So it's a metric you can check, and this is not complete under this metric. You complete it, you get QP. So it should be compared with R, is completion of Q and absolute value. The usual absolute value function, if you complete Q with respect to that, you get R, but if you complete it with respect to this p-adic metric, you get QP for each P. Okay? Now, this is a locally compact abelian group. I mean, it's a field, right? It's a field, so the plus is a locally compact abelian group. So it has a Haar measure, right? So it has a Haar measure. And its Haar measure is very important. Now, there is a way to fix this Haar measure in the following way. There is a compact subset here, which is ZP, so p-adic integers. So this is inverse limit of Z over P and Z. So this is p-adic integers. Okay. So now this, you can show that is actually a subgroup of ZP, like it's a subring of that field. So let me write it like this. So we have this ZP inside QP. So this is p-adic integer. So this is a compact subring. This space is compact because it's a pro-finite group. It's inverse limit of some finite sets. So it's compact, right? So this is a compact subring. So the Haar measure is uniquely fixed if you say that the measure of this subring is 1, because it's compact, and the Haar measure is such that if you fix it on a compact which is non-zero or non-empty interior, then it's fixed, right? So measure, p-adic measure mu, Haar measure on QP is usually fixed. fixed by saying that mu of Zp is equal to 1. It's uniquely fixed as the thing. So it's like a kind of in place the role of interval. But it's much better than unit interval because it's a subring. Unit interval in R is not a subring, but this is a subring. So it's very important. Okay, so here's a nice exercise. Just to make sure you understand the idea of harmony is that this show that mu of measure of PZT is equal to 1 over P. And also measure of P to the n Zp equal to 1 over P to the n. So these are nice. I mean, the only thing is to prove the first one. The second one also we can easily. Yeah. So yes, there are a lot of interesting locally compact abelian groups, and you can do Fourier analysis on them, and these are very important for number theory, not for analysis, but for number theory. Very important. Okay, so this was a side remark. I just wanted to show that this subject has real content. It's not just some easy generalization of known cases. Okay, now we can discuss Poisson summation formula. Any questions, by the way? Okay. Now, so what is Poisson summation formula now in general? So it's the following statement. So Poisson summation. This is the general formulation. So let G be a locally compact abelian group, and H, subset of G, is a closed subgroup. Then for any function f in L1 of G, or any function f belonging to L1 of G, we have the following statement: integral of f of h dh over h, is equal to integral of f hat of chi d chi over G mod H hat. Okay. Right. So I have to say this. Let G, let H. So I'm saying, then after this, I'm saying fix R measures on G and H. Okay. Fix R measures on G and H. Then the statement is that there exists a unique R measure on G mod H. There exists R measure on G mod H hat, actually, such that, this I should have added here before the statement, such that for any function, this holds. So this is because the group is abelian, so this is a locally compact abelian group again. H is closed, so this is good quotient. And you take the dual group. Okay, so let me just write it here, note. This G mod H hat is naturally isomorphic with a space of characters on G belonging to G hat such that the value of this character is constant on H equal to 1. This is more or less obvious. Chi restricted to H is equal to 1. So we can just say we are here integrating over this sort of characters of that nature. Okay, so that's the statement of Poisson summation formula. Now let's see, before I give the proof, let's see how this implies the Poisson summation formulas that we know from lectures that we have. Okay, so,
question.
Yes.
So what role does the Haar measure on G play?
The role on Haar measure. Oh yeah, the Haar measure. Yeah, that's a good question. The Haar measure on G and on H gives us a Haar measure on G mod H, and this Haar measure on the dual is such that it's actually the one that appears in Poisson formula. Remember, for Poisson formula, I said that if I have a group like G mod H in this case, for example, right, with a Haar measure, there exists a unique Haar measure on the dual, right, such that this is the case. So you can say it doesn't play a role because if you believe in the statement, but if you have the Haar measure over there, it's actually that Haar measure that kind of, because we need in order, you see, I mean, the problem is in order to define this hat, we need a Haar measure on G mod H hat. And if you fix a Haar measure on G mod H hat, you have fixed the Haar measure on G mod H itself by Poisson theorem.
And is the Haar measure on G mod H determined by the Haar measure on G and the Haar measure on H? Like, what kind of relation must they satisfy?
So let me get into that after I give some examples. Then you see what's going on.
Okay.
Right. So right. So let me give you some examples now. Okay. Okay, so let's start here. Example 1. So we can take G equal to R. It's a with Lebesgue measure, which is a Haar measure. And let's take H equal to Z. Right. Then G mod H is isomorphic to, well, I mean, R mod Z, of course, is the same as R mod Z. It's a circle, and R mod Z dual the dual, the character group of R mod Z is this is circle is Z. Right? So actually, in this case, the Poisson, I mean the Poisson summation formula in this case is the statement that this is counting measure on H, right? Here is also counting measure, and it's the statement that sum f of n belonging to Z is equal to sum. Well, we have to take the full, but this is just a Fourier transform. I mean, not Fourier transform, it's the Fourier series of f, right? So this is equal to f hat of, say, k belong to Z. So here, the normalization is 1, and you don't see anything. So you don't see any particular feature. But that's exactly, so for example, I said first for any f, when I was proving this, I said for any f in Schwartz class, but the statement is actually more general. I mean, here it's formulated as in L1, but I'm not sure this L1 is enough. We have to have a little more conditions, but that's okay. That's not the point of this discussion. But the point is here. Okay, so this is one case. This is the original Poisson. This is the original Poisson summation formula, which is a special case of that. But now we can change this H now. Let's see what happens if I change H, right? So if you change H, so if you change H, you can take, for example, LZ. I mean, we are going to change the lattice size. Instead of 1, it's going to be L. So is the lattice size is L. The L is positive, right? Just a positive number. So L is lattice size. Then in this case, this result, PSF, is the following: sum f of Ln, right? N belonging to Z is equal to sum. Now, what is this dual group in this case? The dual group is naturally isomorphic to the dual lattice. I mean, this group, see, let me write it R over LZ. Yes, R over LZ. Dual is naturally isomorphic to 1 over LZ. That's what I call dual lattice, right? Dual lattice. Remember, I think we use the notation gamma star, right? So in this case, we check that this is the one. So this is going to be equal to sum f hat of k over L, k belonging to Z. But then the constant, the normalization constant is not 1 anymore. There's a normalization constant here, right? So do you remember what is the normalization constant?
Volume of the lattice.
Dual lattice.
Dual lattice.
Yeah, it's 1 over L, right? The normalization is 1 over L. So that's something that's guaranteed, but each time you have to discover it yourself. The general theorem is proved, doesn't give you what is this, so you have to figure it out. But even more general than that, we worked. So it's actually a good idea to work that more general case. So let us now go to example 3. So we just take G equal to Rn and H equal to gamma. It's a lattice, really. Just a general lattice in Rn, as we discussed before, right? General lattice. Of course, a lattice is a closed subgroup of Rn because it's discrete, so it's closed subgroup. Lattice. And then what we have is that in this case, G mod H hat is our N mod gamma hat. And this, you can easily show that this is isomorphic to gamma star, to the dual lattice. Which we identified, I mean, this is an isomorphism we can prove, so this is the dual lattice in general. So then Poisson summation formula in this case was that sum f of gamma belonging to gamma is equal to sum, okay, there's a coefficient here, so what right hand side of hat K belonging to gamma star. F hat is the Fourier transform of f as a function on the big, so this is really Fourier transform. It's not Fourier, maybe I said Fourier series at one stage. That's Fourier transform really, because it's over all of thing. So that's the one, and then this is 1 over volume of gamma. Yes. And that's the most general Poisson summation formula that I proved before. That's the one for lattices, and we used it to derive the functional equation for theta functions and for Milnor's counterexample. So, what this is, you see, it's a very, very special case of this. By the way, if you can figure out the constant in Plancherel's formula, then you can figure out the constant here, because the constant here is the same from Plancherel's formula. So that's part of the statement. So the constant. That's what. Did you get it, Henry? I mean, we need the measure on G in order to figure out this constant, basically. The Haar measure on G.
Yeah.
Yeah, so we have that. Okay, now how is the proof? This looks very general. So how is the proof going? So let me give you the idea of the proof, because on Monday we are going to generalize this to non-abelian groups and to prove a pre-trace formula for non-abelian groups. And then we further specialize to some particular non-abelian groups, which is